Hi, this is Simon Goda from Doulos, and in this short video I'm going to introduce the Doulos Training course, Developing with Embedded Linux. Before we start examining the course in detail, it's worth spending a few moments looking at where Linux is used in embedded systems, what kind of products are developed using Linux as their operating system. And so we'll do that using some examples of embedded devices from a typical home. The simplest of these, such as a central heating controller or even a smart light bulb, will use a very simple microcontroller such as an ARM Cortex-M0 or even an 8 or 16-bit processor. More complex systems typically will use 32-bit devices and use a real-time operating system to provide more connectivity and functionality. Examples include a standard definition set-top box or an IP phone like you might have on your desk. The most complex devices, using 32 or 64-bit application processors like an ARM Cortex-A9, require multiple applications to be running with high levels of connectivity. So here we're talking about things like smart TVs or modern network-enabled printers and so on. And it's these products which are making use of Linux. Some of the examples you can see here are historical, but they do illustrate the progression that there has been in some products between the different sectors. And here, of course, we're not covering industrial examples or devices from, for example, the automotive sector. A typical modern car will in fact contain numerous embedded systems, from the braking controls through to the sat-nav and entertainment system. It's these latter systems which are increasingly making use of Linux in automotive. Typically, the basic devices will run a C or C++ program on the microcontroller, which will interact with the various peripheral devices and control the system. They are often referred to as bare machine programs, as the application must interact directly with the hardware, the processor and the various connected peripherals, switches, buttons, sensors, displays and so on. In a more complex device, the operating system provides a layer between the hardware and the application, which in some ways makes it easier to program the application, as it doesn't need to know the low-level details of the hardware to be able to run on it. On this more complex device, the program will define a number of different tasks or threads which deal with different parts of the system. Most RTOSs also provide code to drive more complex peripherals like touchscreens or to access the internet via a Wi-Fi connection. The real-time and real-time operating system describes the ability of an RTOS to be able to react to an event within a certain predictable amount of time. And for that reason, they're often used in industrial, automotive, aerospace, defence and so on applications where it's critical that some events are dealt with in a timely fashion. When you press the brake pedal on your car, you expect the brakes to come on. More complex devices behave more like the computer that you have on your desk or the smartphone that you have in your pocket. A complex operating system like Linux allows lots of applications to be run, controlling which one gets more processor time and which run in the background. Many companies are now using Linux as its free and open source software, which means that anyone can make use of the software as long as they share any changes that they make. And this has led to a huge amount of free software being made available. Almost all of the software and applications used on many complex products such as smart TVs, in-car entertainment systems or complex industrial devices is and can be free software. Linux generally, without substantial software engineering effort, will not provide the real-time control that many systems need, which is why we often come across devices which use multiple processors, some running Linux and some using an RTOS. To work with Linux in these complex systems requires knowledge of how to work with the open source software and to make use of the huge amount of freely available tools and software. So as we've seen, Linux is being used more and more in embedded systems, driven by the demands of increasingly more complex devices and the requirements for greater connectivity and multimedia. And working within this environment can be very challenging. As we mentioned, using open source software means there is a vast array of choices to be made for tools and the software that we use. The Doulos Developing with Embedded Linux course provides an overview of the main components of an embedded Linux system: the bootloader, the kernel, the file system and the applications and libraries it contains, and the tools that we need to use on the host development system to work with all of this software. Each part of the system is examined in detail with practical examples of how to configure, compile, run and debug all parts of the software system. The aim is to equip you with the skills you need to develop and maintain products using Linux. Let's now look at the course agenda to give some more details about what you will learn. Once we've introduced the course, we will then go on to look at the possible sources for Linux in your embedded system. Where do you get Linux from? In the anatomy section, we look at the main components of the system and introduce what we will be discussing in detail in the rest of the course. We will then investigate how the Linux kernel, the heart of the operating system, works and how to work with it, including some discussion of how drivers and modules work. Into the second day, we will look at what the options are for debugging the kernel and your drivers and so on, and looking at the information the system can provide to you to help you understand what's going on. We then start looking at applications in detail, looking at the frameworks and tools used to compile applications, and then investigating the tools and tricks available for debugging application code. We finish looking at applications by examining some of the structures of a typical application, looking at how to manage multiple processes and threads, and how processes can communicate with each other and with the kernel itself. Then we take a step back and start to look at things from a system design or system architecture point of view, investigating the options for not only what needs to be in the file system, but also where the file system can be located. Is it in flash memory? Is it on a hard disk drive? Each of these choices has implications for how the system is configured. Then we look at the bootloader, how it is used to actually load the operating system, and how it can be configured to do many other things, such as managing software updates. On the last afternoon, we spent some time looking at the huge variety of tools available for performance monitoring and system tracing, which are invaluable for solving bugs and improving performance in an embedded Linux system. Throughout all of these sections, the lectures are followed up with hands-on practicals where you get to try things out for yourself on a real system, and typically these make up around 50% of the class time. The course is provided in a range of ways. We deliver both traditional face-to-face classes and also via the internet in live online training. Both of these formats are available for public scheduled classes where you can enroll as an individual or in a small group, or for private and on-site classes where we can train an entire team or company in one go. A key element of the training is, of course, the interaction with the trainer and also the other delegates. And it's important to note that this happens even attending remotely as part of a live online training event, as we'll see. For face-to-face training, we use a pre-configured Linux virtual machine as a development environment on the host, so we don't waste any time waiting for software to install. For the practicals, we use Xilinx Zinc-based targets, including MicroZ and ZBoard, which feature a dual ARM Cortex-A9 CPU. Everything we cover is very generic though and can easily be applied to other systems and targets. For the live online version of the training, we use a similar host development environment, but this time installed on a remote server. This allows the delegate and the trainer to access the host, making it easy for us to help with practicals and discuss specific points. Desktops can be shared between the delegate and the trainer and with the whole group, which provides a very inclusive learning environment. For the target, we use a QEMU-based system, which is an emulated ARM processor, which behaves in exactly the same way as a real CPU, meaning that the vast majority of the practicals are identical to those in the face-to-face version. There is some prerequisite knowledge which we feel is important to have before taking this course in order to get the most out of it. Some experience with working with Unix or Linux-based host or desktop systems is definitely really useful, as it means you can focus on the embedded side of things without getting too bogged down in the details of the administrative tasks. We do, though, help bring these skills on as part of the practical exercises. Any experience you have of working with embedded systems is also going to be an advantage, as you'll be familiar with working with a remote target. In order to understand some of the structures and frameworks used by parts of an embedded Linux system, some knowledge of C programming is a must. If you have any doubts about your experience levels or want to ask what we can do to help you satisfy these prerequisites, then please talk to your local Doulos representative or take a look at the Doulos website. Just a little bit more about what other training Doulos offers. So in addition to Doulos' long history in developing and delivering know-how for electronic hardware design and verification, we now offer a range of training solutions for embedded systems and software, including embedded C and C++, Python, and of course, embedded Linux. Alongside this, in the Linux space, we also have courses about Yocto and Linux system security. We're always working hard to develop new and interesting courses, so please visit the Doulos website to find out more.